Usually when we talk about preserving a historical artifact, there is this expectation of absolute airtight precision, like especially in the realm of science.
Oh, absolutely. The standard operating procedure is
Well,
pretty clear. You label the jar, you seal it tight, you put it in some temperature-controlled archive,
right.
and you just trust that a vital piece of history has been permanently secured for future generations, to study.
Exactly. The intention is always meticulous preservation because the scientific community operates on this belief that they are capturing a piece of objective, undeniable truth.
Yeah, you put something under glass, and it basically becomes an anchor point for reality.
Well, that expectation completely falls apart when you step into the world of 19th century neurobiology.
It really does.
Welcome to today's custom-tailored deep dive, where we're starting with a detail from the sources that is highly bizarre, a little morbid, and honestly, deeply ironic.
It's quite the story.
So for over 150 years, scientists carefully preserved and analyzed a very specific human brain in a jar.
A very famous brain,
Right.
supposedly.
Right. They were meticulously logging its folds, its weight, its gray matter density. And all of this was a desperate attempt to find the biological source code of unparalleled, world-changing human genius.
Because they were doing this under the assumption that this particular brain belonged to Carl Friedrich Gauss.
Who is widely considered one of the greatest mathematicians to ever live.
Yeah, and researchers treated this artifact with absolute reverence. I mean, for decades, entire academic papers were published based solely on its topography.
Oh, wow.
Yeah. The scientists examining it fully believed they were mapping the physical hardware of a man who essentially decoded the universe. They were looking for the anatomical signature of mathematics itself.
But it turns out they were just looking at a clerical error.
A massive clerical error.
Yeah, so in 2013, a neurobiologist at the Max Planck Institute was conducting this modern, high-resolution MRI investigation of the specimen, and he discovered a tiny little mix-up.
It's a small one.
Due to a mislabeling error that occurred shortly after the autopsy way back in 1855, the brain they had been reverently studying for a century and a half didn't belong to Gauss at all.
It didn't.
It actually belonged to a completely different guy, a physician named Conrad Heinrich Fuchs, who just happened to die in the exact same town a few months later.
I mean, it is the ultimate historical punchline.
It totally is.
Physical remains of a man who was utterly obsessed with absolute mathematical perfection, a guy who tolerated zero errors in his own work, were completely bungled by some careless archivist just, putting the wrong sticker on the wrong jar.
Okay, let's unpack this. How does a mind capable of unlocking the universe's most complex secrets end up in such a bizarre post-mortem mix-up?
It's a great question.
Based on the comprehensive biographical text you brought in today, our mission for this deep dive is to look past that mislabeled jar. We are going to explore how a working-class kid born in 1777 became the Prince of Mathematicians.
A title he absolutely earned, by the way.
We're talking about a mind that shaped everything from modern map making to how you and I communicate digitally today.
Yeah, his influence is everywhere.
But we also have to unpack the fascinating, highly flawed, and honestly deeply perfectionist human being behind that genius. So let's start with the origins, because he wasn't exactly born into the scientific elite, was he?
Far from it. I mean, to understand his relentless drive for order, you really have to look at the relative chaos of his beginnings.
Right.
Gauss was born in Brunswick, Germany. His father, Gebhard, was a bricklayer, a gardener, a butcher, essentially a man who survived through hard, grueling physical labor.
Not exactly an academic household.
Not at all. Historical accounts describe his dad as pretty rough, dominating, and entirely dismissive of formal education.
And his mother?
His mother, Dorothea, was incredibly supportive, but she was nearly illiterate. So there was no inherited wealth here, no grand library of dusty academic tomes waiting for him in the study.
It sounds like an environment that prioritized sheer survival over abstract thought.
It was an environment of intense practical reality. But his genius defied that reality almost immediately. He was a child prodigy in the truest sense of the word.
Yeah, the sources mention a famous story from his childhood.
Right. It's somewhat apocryphal in its specific details, but historians agree it perfectly illustrates the fundamental architecture of his mind.
Let's hear it.
So his elementary school teacher, a man named J.G. Butner, was dealing with a rowdy classroom and just wanted a break. So he gave the students this incredibly tedious, time-consuming task.
Busy work.
Exactly. He told them to sum all the whole numbers from 1 to 100.
Okay. If you approach that the normal way, just adding 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, that is going to take an 8-year-old a massive amount of time.
Oh, absolutely.
And with a very high probability of making a simple arithmetic mistake somewhere around, like, the number 47.
Right. While the rest of the class was probably groaning and scribbling frantically on their slates, Gauss just walked up to the teacher's desk within seconds. Yeah. And he handed in his slate with a single number written on it. 50-50.
5050, just like that.
Just like that. He hadn't done the brute force addition. He instinctively saw the underlying structural symmetry of the numbers.
How did his brain even do that?
He realized that if you pair the numbers up from the outside edges moving inward, so 1 plus 100 is 101.
Okay.
2 plus 99 is 101. 3 plus 98 is 101.
Oh, I see where this is going.
Right. You end up with exactly 50 pairs of 101. So he just multiplied 50 by 101 in his head.
That is wild. He didn't just solve the problem. He invented a structural shortcut by seeing the invisible architecture of the math.
Exactly.
He saw the scaffolding that nobody else even knew was there. And that concept of scaffolding gets right to the core of his lifelong philosophy, doesn't it? That absolute, almost paralyzing demand for elegance.
It really does. He eventually adopted a personal seal featuring a tree with only a few pieces of fruit on it, accompanied by a motto that governed his entire professional life.
Pauca said matura.
Yes, which translates to few but ripe. He absolutely refused to publish any piece of work that he considered incomplete, messy, or open to criticism.
Which is pretty rare for scientists, right?
It is. If we look at legendary mathematicians who came before him, like Leonhard Euler, their approach was entirely different.
How so?
Euler would often publish his entire thought process. He would show the mathematical dead ends he went down, his mistakes, the messy step-by-step journey of discovery.
Okay, I look at that like an architect building a magnificent skyscraper. Euler is the architect who finishes the building but leaves the blueprints on the table and the scaffolding up outside, so every passing student can see exactly how the building was constructed.
That's a great analogy.
But then Gauss builds the exact same magnificent skyscraper. But then he takes away all the scaffolding, sweeps up the dust, locks the door, and refuses to let anyone look at it until it appears as if it just magically dropped from the sky.
Perfectly said.
But, I mean, doesn't that rob future learners of the chance to see how a genius actually works? It makes the science feel like impenetrable magic rather than a shared step-by-step human journey.
What's fascinating here is that his perfectionism didn't just frustrate the students trying to learn from him. It caused massive lifelong conflicts with his contemporaries.
Really, like drama with other mathematicians?
Oh, constant drama. Because he hid his scaffolding and refused to publish his early developing ideas, he was constantly embroiled in bitter priority disputes.
Fighting over who discovered what first.
Exactly, because Gauss held a very specific definition of scientific priority. To him, it meant the first to discover the truth in your own mind.
Not the first to publish it in a journal.
Right, so time and time again, another brilliant mathematician would proudly publish a groundbreaking new theorem, and Gauss would essentially write them a letter saying, "Oh yes, I knew that a decade ago, I have it in my private diary, I just didn't think it was ripe enough to print."
Wow, that is incredibly arrogant. But that attitude perfectly sets the stage for the story of the dwarf planet Ceres. Because this internal demand for absolute certainty eventually pushed Gauss to mathematically map the literal heavens.
The Ceres story is an incredible collision of high-level theoretical genius and just desperate practical necessity.
Set the scene for us.
So in 1801, an Italian astronomer named Giuseppe Piazzi discovered a new celestial object moving through the night sky. He initially thought it was a comet, then realized it might be a planet.
And today we classify Ceres as a dwarf planet in the asteroid belt, right?
Correct. But the problem back then was Piazzi could only track it for a very short window of time, about 41 days before its orbit carried it behind the glare of the sun.
It just vanished.
It vanished.
So if the astronomical math of 1801 couldn't predict where the planet would go, what did Gauss do differently? Did he just have access to better telescope data than the veteran astronomers?
No. Not at all. He had the exact same limited data points as everyone else. But the math required to find Ceres based on such a tiny sliver of observation resulted in an equation of the 8th degree.
Which means what exactly?
It means it was a chaotic mess of variables that the standard tools of the era simply couldn't handle.
Okay.
But Gauss, who was only in his early 20s at this point, decided to tackle the problem anyway. He locked himself away and used his own comprehensive approximation methods to predict exactly where Ceres would reappear on the other side of the sun.
And did it work?
Oh, perfectly. When astronomers nervously pointed their telescopes at his predicted coordinates months later, there it was, accurate to within a half degree.
That is unbelievable. So how did he tame that chaotic mess of data? I know the source mentions a specific secret weapon he used called the method of least squares, but how does that actually work in practice?
Think of it like trying to draw a perfectly straight line through a messy, buzzing swarm of bees.
Okay, bees. I'm with you.
If you take a bunch of real-world measurements, like telescope sightings of a planet through a blurry atmosphere, the data points are going to be scattered and slightly inaccurate, just like those buzzing bees.
Right, because of weather and human error?
Exactly. Least squares is a mathematical mechanism for drawing a single line through that swarm so that the total combined distance from the line to every single individual bee is as small as mathematically possible.
Oh, I see.
It minimizes the impact of the errors, allowing you to find the true trajectory hidden inside the messy data.
Here's where it gets really interesting. Adrien Marie Legendre, a highly respected French mathematician, officially published the method of least squares in 1805.
He did.
But 4 years later, in 1809, Gauss finally publishes his magnum opus on celestial mechanics, predicts the orbit of Ceres, and casually drops a note essentially saying, by the way, I've been using this least squares method since 1794. Legendre's work is nice, but it's mine.
Yep, the classic Gauss move.
I mean, if you don't publish the concept, do you really get to claim the credit? It's a bit like sitting in the back of a comedy club and whispering, I totally thought of that punchline, after the comedian on stage gets the huge laugh.
It sparked a fierce international rivalry. Legendre was deeply offended, and understandably so.
I would be too.
But setting the historical drama aside, the sheer impact of the least squares mechanism cannot be overstated. It is the absolute bedrock of modern statistics and data science.
So it's still used today?
Oh, everywhere. Anytime you look at a corporate scatter plot today and see a line of best fit drawn through a cloud of data points predicting future sales or population growth, you are looking at the direct legacy of Gauss trying to find a missing space rock. He created these monumental, world-changing theoretical tools just to solve a practical annoyance.
And his obsession with spatial precision didn't stop with the heavens, did it? Once you successfully map the sky, you become the logical choice to map the ground.
Yeah, makes sense.
Because eventually, the King of Hanover realizes he needs a highly accurate map of his kingdom, and he sends his most famous mind out into the mud to do it.
This brings us to the Geodetic Survey of Hanover, which consumed a massive portion of his life from 1820 to 1844.
That is a long time in the mud.
It was exhausting. Gauss wasn't just sitting at a pristine desk in an observatory anymore. He was out in the dense, forested terrain of the Lunenburg Heath, literally measuring the curvature of the Earth.
And he runs into a problem,
A grueling physical problem. To map the kingdom, he has to measure massive triangles across the landscape over huge distances, sometimes up to 66 miles apart. But through the hazy German atmosphere, he simply can't clearly see the distant measurement points.
So rather than throwing his hands up or waiting for clearer weather, he just invents a totally new piece of hardware. He creates the heliotrope.
The heliotrope was a brilliantly simple solution to a deeply frustrating practical problem.
What was it exactly?
It was a device that used a combination of movable mirrors and a small telescope to catch the sun's rays and reflect them as a concentrated beam directly to the other surveying stations miles away.
So it's like a massive signal mirror.
Yes. It turned a hazy, invisible target into a blazing point of light. But the physical exhaustion of measuring the curved surface of the Earth day after day sparked a theoretical revolution in his mind.
Which led to?
It led to what he proudly called the theorema egregium, or the remarkable theorem.
This is one of those concepts that breaks your brain a little bit when you first encounter it in the text. He proved that the curvature of a surface is an intrinsic property, meaning you don't need to be floating out in 3D space looking down at a sphere from the outside to know it's curved.
Let me give you a visualization. If you imagine a tiny, highly intelligent bug walking on the surface of a giant sphere.
Okay, I've got the bug.
That bug can't look up and see the whole shape. But according to Gauss's math, if that bug just walks around drawing triangles on the ground and measuring the interior angles, it will find that the angles add up to more than 180 degrees.
Which wouldn't happen on a flat piece of paper.
Exactly. The bug can mathematically prove it is living on a curved surface entirely from the inside without ever stepping off it.
And the because right around this time, he pivots to electromagnetism with a physicist named Wilhelm Weber. And in 1833, they build the first electromechanical telegraph.
They did. They strung a wire over the rooftops of Göttingen, a distance of about a mile and a half, to connect the astronomical observatory where Gauss worked directly to the Physics Institute where Weber was conducting his experiments.
See, initially when I read that, I thought it was just a quirky historical footnote. Two geniuses setting up a private Victorian-era text messaging system just so they didn't have to walk across town in the rain to chat.
Right. It sounds like a hobby.
Exactly. But it wasn't just a fun side project, was it? It was a symptom of his insatiable need for data. He didn't invent it to socialize. He invented it because his brain simply couldn't tolerate the latency of walking across town when there was magnetic data waiting to be processed.
If we connect this to the bigger picture, you see exactly how that need for immediate data scaled up. Their work in magnetism wasn't just a local experiment. It was a global ambition.
What did they do next?
Gauss and Weber went on to create the Magnetic Association. This was an international network of observatories all over the world, from Europe to the Americas, measuring the Earth's magnetic field simultaneously.
Wow.
Gauss developed standardized methods and invented a specific type of magnetometer that allowed, for the first time, an absolute measurement of the Earth's magnetic force.
He is basically birthing the modern field of geophysics out of thin air. He is coordinating scientists across continents to see the invisible magnetic forces that govern the planet.
He was everywhere all at once.
Up to this point, the historical record paints a picture of a guy who is practically omniscient. He understands the heavens, he maps the earth, he controls invisible electromagnetic forces.
Yeah.
But when you look at how he related to the actual messy human beings living inside his own house, it is a totally different, much darker story.
The contrast is incredibly stark. While he was mapping the universe, his contemporaries frequently described him as having a difficult, highly critical, and grumpy character.
Yeah, one famous description from the time called him an unapproachable Olympian sitting enthroned on the summit of science.
He was deeply isolated, and his family life was repeatedly overshadowed by profound, destabilizing tragedy.
The sources mentioned a lot of loss.
So much loss. His first wife, Johanna, whom he loved deeply and passionately, died suddenly just weeks after giving birth to their third child. He was entirely devastated.
And then his second wife.
His second wife, Minna, suffered from severe, debilitating tuberculosis for over a decade before she finally passed away.
It's heartbreaking. And the source material indicates that his relationship with his children, particularly his sons, was incredibly strained.
Strained is putting it mildly. Take his son Eugen, for example.
Okay.
Eugen was highly talented in computation and had a real gift for languages. He desperately wanted to study philology, which is the study of language history and literature.
That seems like a respectable pursuit.
You'd think. But Gauss, this man forged in practical labor and obsessed with rigid scientific order, absolutely refused. He forced Eugen to study law instead, believing it was a more practical, rigorous path.
That never goes well.
It didn't. Eugen predictably rebelled against this control. He ran up severe gambling debts, caused a massive public scandal in the university town of Göttingen, and ultimately ended up fleeing to the United States.
And Gauss's reaction to his son fleeing the country wasn't to chase after him or try to mend the relationship. He just cut off his financial support entirely.
Completely cut him off.
Eugen ended up in Missouri working as a businessman, completely alienated from his father. It's so cold. And then, as Gauss ages into his twilight years, we see this strange behavior where his need to quantify everything just sort of spirals into the absurd.
It really does. In his later years, he obsessively collected and cataloged completely useless numerical data.
Like what?
He would count the exact number of steps and the specific variations of paths it took to walk from his home to certain routine places in town. He would calculate his acquaintances' exact ages in days.
In days?
Yeah. He actually took the time to send a letter to the famous explorer Alexander von Humboldt for the sole purpose of congratulating him on reaching the exact age calculated down to the day that Isaac Newton was when he died.
So what does this all mean? How do we reconcile this supreme, universe-unlocking intelligence with a man who alienates his own flesh and blood and spends his golden years meticulously counting his steps? It's almost as if he was trying to apply mathematical certainty to a world that was rapidly slipping away from his control.
That is the ultimate tragedy of his genius. Gauss was famously quoted as saying God arithmetizes.
Meaning?
He fundamentally believed the universe was built on strict order, logic, and mathematics. His mind was uniquely, brilliantly built to organize and quantify everything he touched. But human relationships, the messy reality of grief, trauma, and raising a rebellious teenager, they simply don't follow clean, predictable formulas.
You cannot apply the method of least squares to a broken heart.
Exactly. And because he couldn't quantify the human experience, the very brilliance that allowed him to understand the universe left him profoundly isolated from the people living in it.
He could mathematically predict the exact location of a missing planet millions of miles away, but he couldn't figure out how to connect with the sun sitting right across the dinner table.
It is incredibly tragic.
It is. But for you listening right now, it is worth taking a moment to realize just how much Gauss's isolated, perfectionist mind still dictates the modern, everyday world you navigate.
Oh, his mathematical fingerprints are practically inescapable.
If you pull up a GPS map on your phone to find a new restaurant, you are relying on the intrinsic geometry and geodetic principles he established out in the mud of Hanover.
Absolutely.
If you are sitting in a corporate meeting relying on a statistical model or a bell curve to make a financial decision, you are using the precise tools he formalized to track asteroids. Hell, if you are listening to this digital audio stream right now, you are benefiting from his genius. Because back in 1805, Gauss invented the algorithm for what we now call the Fast Fourier Transform.
Which is an incredibly vital concept for modern computing.
Right. To explain how the Fourier transform works, think of it like mathematically unbaking a cake.
Unbaking a cake, I like that.
Yeah. It takes a complex, messy digital signal like the sound wave of my voice right now and perfectly separates it out into its basic, simple frequency ingredients. This is the exact math that allows digital audio and video to be compressed, transmitted over the internet, and reassembled in your headphones.
And he did this way before computers.
A full 160 years before it was officially discovered for modern computer science. You are constantly interacting with the ghost of Gauss.
He truly was the central architect for the development of 19th century mathematics. But he built that architecture on his own highly restrictive, secretive terms.
So the next time you are feeling paralyzed by perfectionism, like you can't share a project at work or a creative idea because it's just not ripe enough, remember the heavy personal and historical cost of Gauss's Pauca sed matura. Sometimes you just need to leave the scaffolding up and let people see your messy process.
And this raises an important question and a really fascinating what if for the history of science.
What's that?
Well, if Gauss hadn't been so fiercely obsessed with only publishing flawless, complete masterpieces, if he had openly shared his messy, half-finished ideas on non-Euclidean geometry, the radical math that deals with curved space decades earlier, instead of hoarding those breakthroughs in his private diaries out of fear of criticism.
Oh, wow.
How much faster would physics have advanced? This is the exact math Albert Einstein eventually needed to formulate the theory of general relativity.
That's a huge implication.
It is. Did the Prince of Mathematicians' paralyzing perfectionism actually delay our understanding of the universe by an entire century?